Hello, my name is Richard Albayaty. I'm a first year PhD student in the ECE department at the University of Florida. This presentation is on gesture recognition using motion sensor data. For reference material for the topics encompassed by this presentation, I provided them in the accompanying paper. For questions regarding the material covered in this presentation, please email me at the displayed email address. First, I'd like to talk about the overview of this presentation. I'll be discussing what gesture recognition actually is. I'll talk some of the different approaches that have been or could have been used for gesture recognition from current and previous literature. I'll provide an introduction to the problem and what will be necessary to train a hidden Markov model. I'll talk about the experiments that were done and provide feedback on my results. And finally, I'll offer a conclusion of the results and a look forward with this particular research. A gesture is a type of bodily motion that contains more information than what the actual motion itself contains. The gesture is often used in day-to-day interactions to supplement verbal communications with a more concise and meaningful intelligence. Examples of gestures are waving, rolling one's eyes, pointing, or the so-so motion of the hand to signify an average response. Recognizing gestures requires either constantly monitoring the input streams of communications from others or waiting for cues that are often followed by gestures. This seems to be second nature to humans, but devices of technology are not readily equipped with the advanced processing capabilities of the brain. Technology can benefit from the use of gestures, and that many meaningful commands or meanings can be combined into a single gesture, both saving the user time and allowing for a more streamlined feel for the use of said technology. But how do we address the problem of getting devices to recognize gestures in either real-time or, quote, offline, which is doing so from pre-collected data? To address this, we need to first discuss a machine perception of gestures. This can be broadly defined in three categories, which are listed as either being supervised learning, unsupervised learning, or reinforcement learning. The first of which, supervised learning, requires there be labels. Labels are definitions for an output of a given input-output relationship. For instance, if I wave my hand, then the correct label for that would be a wave. An incorrect label for that would be a nod, because my waving is not a nod. In unsupervised learning, no such labels are affixed to the data, so when you're given an input and an output data set, you have no idea what is correspondent in either, and another aspect of the problem is to actually classify the data in meaningful ways. In reinforcement learning, the model dynamics aren't actually known either. What this means is that you don't actually know a meaningful relationship to go from input to output, nor do you have the labels. Some different types of algorithms that have been used and are currently being used to perform gesture recognition are finite state machines, dynamic time warping, hidden Markov models, support vector machines, artificial neural networks, fuzzy logic, and slow feature analysis. Of these, only a subset was addressed in this paper. However, many of these, to include more, are extremely beneficial and useful in the gesture recognition task. Listed now, 1 through 10, are the different gestures that were used in this work. There's an additional gesture, the quote still gesture, where the data was collected from a resting sensor to help normalize the data and give something that was significantly different than all the other gestures to add as one more gesture label. As you can see in these gestures, the black dot is the starting position and the arrow points in the direction of movement and is listed in the endpoint of each of the movements. We have a square, circle, motion right, motion left, motion up, motion down, somewhat of a theta sign, a play sign, an isosceles triangle, and a star as the gestures listed. For the data sets that were used in my experimentations, I collected data on 10 different samples of each gesture. So having 11 gestures and 10 samples per gesture, I obtained a total of 110 data sets. I will also be varying the amounts of training and testing sets from this 110 total sets, and that will be covered in the later analysis of the variation of the training data percentages. Additional testing sets I obtained from another person in order to test the robustness of the model that was developed using the hidden Markov model process. 4 high-level experiments were conducted using hidden Markov models. The first being multiple user recognition. And what this is I wanted to train the models with gestures that I myself created and then test the models with gestures that were obtained from another user to see how robust the system is. The second experiment is using more sensor data types, and by that I mean instead of using accelerometer data strictly for the training of the hidden Markov models for the gestures, what would the effect be if I added more data on both the robustness of the classification and also the length of time it takes the algorithm to run? Thirdly, I'd like to vary the amounts of the training data to see the effects on the classification errors. And lastly, on the fourth experiment, I'd like to see how doing these different things affects the runtime of the algorithm. A note on the representation of results in this work: I adopted the confusion matrix, which is a 2D or a 3D representation, and it's represented as either count numbers or a percentage of classification, and I'll give examples of these in the next couple slides. This is an example of a 2D confusion matrix, and as you can see on the diagonal we have a listing of ones. The horizontal is labeled 1 to 11, and the vertical is labeled 1 to 11. You can take the vertical axis as the true labels and the horizontal axis as the classification. So the diagonal corresponds to a true classification, where the true label was vertical and the classified label was the horizontal. Any off-diagonal entries correspond to misclassifications. This is a representation on the left of the 3D version of the confusion matrix, where we're using the count, the number of classifications, and on the right is the exact same representation, except instead of counts it is using a percent classification, where the entire matrix has just been normalized. For the first experiment, where I was questioning the robustness of the algorithm to varying amounts of users, on the left we can see that there is only one off-diagonal entry, and what this represents is that only one out of all of the test gestures was misclassified. All of the others, as you can see, have been classified correctly. On the right we have many off-diagonal entries, and this corresponds to the second user's test gestures not having been classified correctly. So this is just representation of the fact that the hidden Markov model in the implementation that I use is not robust to different users with a single user's test data for training. The second experiment, where I wanted to see the effect of adding in gyroscope measurements on top of the acceleration measurements in order to train the models and then subsequently test the models. As you can see in the first two horizontal rows is a representation of the first user's test gesture classification rate, and then the second is the second user's gesture classification rate. And as you can see in the vertical columns, we have a different amount of training data percentage, starting from a 40% of the total data set and ending in a 90% of the total data set. And as you increase the amount of training data, both the first and second user test results provide smaller misclassification rates. And as you can see from adding the gyroscope from the second two rows, the effect initially is more errors as shown in the column of the 40% training data rate, but as you progress and get more training data, it's shown that for a single user training and a single user test, you actually have significantly better classification rates. The third experiment was training data dependence. I wanted to see the dependence on the percentage of the total data set's training data that was provided to actually train the hidden Markov models. And as you can see, this graph shows that the optimal, this table shows that the optimal classification rate lied at about the 70% training data mark. And the reason for this, instead of a 90% being the best, I do believe is from the fact that I'm only using 10 samples per set. So a 70% training data corresponds to having 7 samples in the training data, which only leaves 3 samples for testing. So a 90% would only offer 1 example per gesture for testing. If I were to do a percentage over a larger amount of data sets, I do believe that this number would be high or lower misclassification for 90%. So for runtime variation, I noted that over 2 different runs, there was a nearly negligible difference in the amount of runtime. The reason that there was a difference is because of the fact that I'm using Gaussian hidden Markov models, so there is some inherent variability in the actual data and the construction of the models, as well as the performance of the models. But the results of this experiment were that with the data set that I had, varying the training data percentage offered linear time increases. Some of the problems that were encountered in my doing this project, I noticed that if you use too small a training sets compared to the gesture dictionary size, namely having 11 gestures and using only 2 gestures for training versus using 7 gestures for training, offers significant improvements. So lower amounts of training data definitely increase the misclassification rate. Also, as I suggested earlier, each run contained randomness. The results varied between iterations, so to get good analysis of data, many iterations would have to be run, and the results would need to be averaged to take advantage of the central limit theorem to actually provide meaningful data per run. Now I'm going to show an example of the MATLAB simulation, but I will skip the data acquisition and the formatting steps in order to save time. So right now what I'll show you is the actual gestures plotted. So as these pop up, you'll see this is the square, this is the circle. The red corresponds to the x-axis, the green corresponds to the y-axis, and the black corresponds to the z-axis. And on the left we have the acceleration data, and on the right we have the gyroscope data. Each one of these plots that are popping up is a different motion. And as you can see, there is variability in each gesture. Temporally, you can see a shift, and then also there are some amplitude variations in each of the gestures. And the whole intent of creating these models is to accommodate for both temporal and spatial differences in gestures. Now I'll run one iteration of the algorithm, and while the algorithm is running, I'll discuss different sections of the algorithm. So as we can see, for each of the gestures, we need to create a hidden Markov model. This is going to take some time, that's why I will talk about each section. What's shown here is the log likelihoods of each iteration, and as this approaches some predefined difference, so a delta between iterations, once it gets less than that delta, it converges, so to speak, and stops the algorithm. In this test case, I'm actually using both the accelerometer and the gyroscope measurement. So I have an observation space of dimension 6. This section corresponds to the actual creation of the Markov models. This section corresponds to the Markov model testing, where I take whatever is left of the total data set from the training and I use them as test sets. This section is where I take the second user's data and I test it on the given models. And then finally I have a section that corresponds to running the algorithm's outputs. Let's check the status. We are at 8, so we have a few more. Different types of examples were created. For instance, this here, I won't get into the code, but what I did with this is I created additional sample sets with using one of the training sets and adding Gaussian noise to it. This is done in some of the literature, and I tested it, but not extensively enough to include in this presentation. And this is the exact same algorithm I'm showing here that's currently running, except I do not include the gesture gyroscope measurements, as can be seen by the lower dimensionality of the observation space. Now the graphs are being formulated and plotted. What we'll output here will be the confusion matrix in tabular form, as we can see, and then there will be some runtime analysis. These figures show on the left here a representation of the test data from the single user. As you can see, there were only 2 classifications that were wrong, and all the rest lie on the diagonal. Here on the second user's test data, we see that very few actually lie on the diagonal, while a lot lie on the off diagonal, which correspond to misclassifications. And from the orange color, we can see that there were many misclassifications onto one of the gestures, meaning that one of the gestures dominated this model. And this is a cumulative representation of both of those to give the total classification percentages. And as you can see, using the single user and the double user data, we do have a significant amount of proper classifications, but we do have the meandering misclassifications. So in conclusion, I've shown that the Hidden-Markov model is sensitive to user training data, and by that I mean a second user's training data will throw off the model. I've shown that the Hidden-Markov model gains from additional gyroscope data instead of just the accelerometer data. Also, the more training data, the better, which is usually in general practice the case. However, it was shown for the Hidden-Markov model to be so as well. And we've seen from the limited amount of training data, our total data that I provided, that the Hidden-Markov model operates linearly in time as you vary the amount of training samples. A potential for future work would include signal denoising, and this would be implemented in the pre-processing phase prior to the actual generation of the Hidden-Markov models. This could aid in the actual classification error rates, increasing the classification rates, lowering the misclassification rates. Additionally, an exhaustive algorithm comparison could be done. In other literature, fewer subsets of different algorithms were compared, but there doesn't appear to exist an entirely exhaustive comparison of all the different gesture algorithms and their performances. Having done this would allow for a user to more easily pick application-specific uses based on their operating strengths and weaknesses. Thank you for your time. I do hope that this presentation has been both informative and interesting. Have a great day, and go Gators!